So theoretically, we have seen that. Let's check it mathematically that what is actual loss of basically generator and what is the actual loss of the discriminator. So generally, in case of generative adversarial network models, that is called GAN, we use binary cross entropy loss function loss function. And what is that? It is L of y hat comma y is equal to y log y hat plus 1 minus y log 1 minus y hat. What is y? Y is the actual data sample label. Y is the label of actual data sample, or you can say that actual output. And what is y hat? Y hat is the predicted one. Y hat is the predicted one. Got it? So if I talk about discriminator, that is called as D. So the discriminator is getting the data from how many sources? From two sources.
Ashish sir, your screen is not visible.
My screen is not visible. Okay, okay,
Yes.
okay. Just now is it visible?
Yes, sir. Yes.
Okay. So basically, I was talking about this loss function that is called as binary cross entropy loss, and where it is equal to y L y hat comma y equal to y log y hat plus 1 minus y log y minus y hat. What is this y? Y is actually the actual data sample, actual data label, you can say, or the actual output. And what is this y hat? Y hat is the predicted one, means predicted by my model. Now, first of all, discuss the loss function of the discriminator, and then I will discuss the loss function of the generator. So, for example, I have this discriminator D. D is getting the input from two sources. One is from the real data samples that is called as X, and one is the generated one. One is the data samples which are generated by the generators, that is called Z of C. Got it? So it is getting data from two samples. And what is my expectation? My expectation is that this Y is the actual data sample, and for this, it should for the actual data sample, it should produce output as 1, and for the generated data sample, it should produce output as 0. So discriminator model D is a binary classifier which produces the value between 0 and 1. One should be produced, my expectation is one should be given for the real input sample, and it should give 0 for the fake data sample. This is my expectation. Now let's check. If we talk about the labels of the data which are coming from p data x, what is this p data x? Original data distribution, probability distribution of the original data. For this, y should be maximum value of y should be 1 and minimum should be 0 because this is probability distribution. So what should be the value of y? Y will be equal to 1. That is the actual. What is y hat? Y hat will be equal to dx. Dx is the probability distribution or the output given by the output layer of the basically discriminator model. So for example, we are using sigmoid function as output layer. So it is going to produce the value between 0 and 1. So dx is the basically output of the last layer of the discriminator model. Got it? So if I'll put these values in this particular loss function, I have to put dx at the place of y hat. So I have, so in the same equation, just check. This is the original equation, and I am putting the values of the loss function. So what is this? Dx is the basically output of the last layer of the discriminator. What is 1? 1 is the value of y, that is the actual output, and this is the predicted one. Got it? And in the right hand side, uh, there are two terms. This is first term and this is second term. So the second term will become 0 because 1 minus 1, 1 minus 1, this is 1, because y is the actual output, that is 1, that we already know. So this will become 0. So the second term will become 0, and it will be equal to log of dx. This is called as a. I have named this equation as a. So this is loss for the data coming from the real sample. And what is the second source of the data? This is the first source of the data. And what about the second source of the data? That is the generated one. So if I talk about the second source of the data, means the data which is coming from generator G, the actual label is y is 0. And what is y hat? Y hat is the whatever the input, that is z of z, that we have given to discriminator, and it is going to produce the value between 0 and 1. So in this case, the first term will become 0. The first term will become 0 for the data coming from G, and the second term will become 0 for the data coming from the real source. Got it? So it is going to become y hat will be d of z, comma, this is the actual label, that is called 0, and this will be equal to 0 plus 1 minus this, because actual term y is 0. So this one first term will become 0. So it will be like this. So I have termed this as b. So what will be the total loss for the discriminator? Total loss for discriminator, it will be equal to a plus b. So a plus b means log of d of x plus b means log of 1 minus d of z. I hope this is very simple mathematics, and you are getting it if you have listened the lecture carefully. So you can just understand this concept very easily, because this is simple mathematical equation. I have just put the value inside this. Now this was about the discriminator. Discriminator is getting the data from the two sources. One is the real and one is the fake one. For real, this is the equation, and for the fake, this is the equation. I have both. I did both. So this is the loss of the discriminator. So this is the loss if it is basically misclassifying the real images, and this is the loss if it is classifying the fake images. Got it? If it is misclassifying the real images, this is the loss, and this is the basically loss if it is misclassifying the fake images. The idea is quite clear. Now, what about the generator? What are the intentions of the generator? The intentions of the generator is that generator wants that whatever the discriminator is giving, that this it should be equal to 1. This is the intention of the generator. If this will be equal to 1, that means discriminator has misclassified. So discriminator wants, the generator wants this. Now if I talk about the equation, I am just updating the same equation that I have derived here, that in case of generator, this log of dx, this doesn't have to do anything with the generator, because this is dx is the function of the discriminator. So generator has no role in this one. Got it? I'm talking about the same equation. But in this case, in the second term, discriminator has the role. And what is the generator has the role? What is the role of the generator? Generator will try to make this as 1. Generator will try to make this as 1. Why it is so? Because in order to fool it, So if you plot the graph of generator, don't have to do anything with this one, just cut it. If you plot the graph of uh, like 1 minus this, so it will become like this, it will become like this. And generator, what generator wants, generator wants that this d of z should be equal to 1. And when this will be equal to 1, that means discriminator is failed. Why it is? Because discriminator should tell this as 0. But when discriminator will be failed, then this is equal to 1. And when this will be equal to 1, if you plot the graph, then at this point, when this d of g is equal to 1, then this graph will have the minimum value. So whenever this term has the minima, when this term will achieve minima, then this will go near to 1. This is quite clear mathematically. When this will achieve minima, then this will tend to 1. So the objective of the generator is quite clear. Objective of the generator is to minimize this term, because when it will have the minimum value, then it will tend to 1. And when it will tend to 1, discriminator is failed, because discriminator should give it 0, because it is generated by can. Now if we talk about the basically uh, discriminator model, discriminator, what discriminator should do, discriminator should give the value of dx, that is original data, as 1, as 1, and this as 0. So when this will be 1, because this is the probability, so this is the maxima. Or if you want to plot the graph, we can just show that if you want to plot the graph of this function, so this is basically kind of point. This is the graph of log of dx. Got it? So when it will become 1, when dx is 1, then the discriminator is successful. And if it want to successful, I am not going to talk about this point, because I am talking about the probability value. So I have to just stop it at 1. That means it should have maximum value. So this is the value of 1. It will be 1 when this is maximum. So discriminator tries to basically maximize it, uh, and uh, mm, and generator tries to basically minimize it. So if we plot, if we just club these two equations and want to plot it, then we can say that this equation, that is log of d of x plus log of 1 minus d of z of z. So this is the overall equation, where generator tries to minimize it and a discriminator tries to maximize it. This is the same thing, because d wants to make it 1, this is the maximum value, and generator wants to just minimize it, because generator don't have to do anything with this term, but it wants to make it 1. And when this will be 1, this overall term will be minimum. Got it? So we are not talking about the one sample, rather this is the loss for the one sample. We have to minimize the cumulative loss. So if I talk the cumulative loss, we can say that it is like basically sum of uh, log of dx. So this basically means that I am taking the sum of the loss from all the functions. It is same like in the case of regression, you just club the distance between the real and the predicted data sample from each of this. So here, what is where from where x will belong? X will belong from the probability distribution of the real data. And here there is no x, rather it is generated data sample. So this z will belongs to probability distribution of the synthetic data set. Got it? So this is the overall story of the generative adversarial network, how these models are trained, and what are the intentions behind it, and how the loss is calculated, and how to train the model, and how to get the basically expected output kind of thing. Now, if I talk about the training process and the probability distribution model, so we can say that in the initial phase, this is the basically real data set, and this is the generated data set. So the real data and the generated data are very far from each other. So this is not the actual data, rather the data distribution, probability distribution of the data, probability distribution of the data. So the probability distribution, as we can see that in the initial iteration, just for visualization, in the initial iterations, this probability data distribution of the original data and the generated data is very far from each other. And so if I have the classifier which is making a cross line between these both the data sets, so D is very easily able to just classify to make a line between this and this. The job of discriminator is easy. By the course of time, if this generated PZ of X becomes a little bit close to a probability distribution of the original data X, so it is a kind of sigmoid function. So it is now a little bit easy, but some competition generator is given. At this point, this is coming even more close to this one, so it is now becoming difficult for the discriminator to discriminate it. But after the course of time, if it is had clearly overlapped, then it's become very difficult for the basically discriminator to in order to discriminate between the original and the distributed data, because they are basically overlapped with each other kind of thing. Now if I want to visualize that how the things go with the course of iteration, you can say that uh, generator G starts with the total pure noise. It starts with the pure noise, and after few epochs, you can say that this noise is converted into this form, and after 10 epochs might be possible, this is converted to this form. It has some clarity, some visibility, and after 70 epochs, you can say that it may come in this form. So by the course of iterations, the model just keep on updating itself, and we have the images of different categories. So it is not necessary that we have to input the same category of images kind of things. Now let us discuss that what are the problems with the GAN. What are the problems with the GAN? So if we want to just know the problems with the GAN, so we can say that the getting this probability distribution Px is not that much straightforward. If I talk about the vanilla GANs, that means the original GAN that has been given by the Goodfellow. So it was just using MLP, that is multi-layer perceptron. So it is not good for generating the very high or complex images. We can just use it for the training or education kind of purposes to generate some simple problems. Why it is so? Because the training is not that easy because of the non-convergence and mod collapse problem. And someone was also asking some question that what happened if we keep on training the generator D and discriminator D at the same time. If you will perform training simultaneously, then you may occur with both, and then you may just encounter with both the problems, non-convergence and mod collapse. We don't want the discriminator that much efficient in the initial phase, such that generator is not able to uh, ever beat the discriminator, or we don't want the discriminator so weak at the initial stage so that generator should not be able to update itself. So you may encounter both the problem that is called as non-convergence and mod collapse. Why it is so? Because loss function will keep on oscillating. It will not be able to converge. Why it is so? Let us discuss. Let us see some problem. Because we are having the problem which is kind of min max in nature. And what is min max in nature? Let us check with some example. So this is a kind of min max problem. So for example, if I have a function like x dot y, where one function is want to minimize this xy and one function want to maximize it. So for example, I am in state 1. What happens during the training? So I have taken the value of x greater than value 0 and y greater than 0. Then v is basically positive. V is greater than 0. That is my function. And one wants to minimize it. At the same time, other wants to maximize it. I have just increased the y and decreased the x. Because other function is just want to minimize it. Might be possible generator wants to minimize it and discriminator wants to maximize it. So generator will try to pull the value of y. So for example, I did x less than 0 and y greater than 0. So this will come greater than 0. And again in the state 3, another one wants to just increase it. It has just decreased the value of y, it become this greater than 0. Again this and this become. So this will keep on oscillating. If you can see this diagram, then what will happen? I want this product x and y. So if I have this line as y and this red line as x and this black as xy, so my intentions are to make a balance between this and this. But what happens? It keeps on oscillating. If I am decreasing it, it is increasing. If I am increasing it, it is decreasing like this. So it is basically oscillating and creating a problem for us, and not it is not basically converging. So what is mod collapse problem? In the mod collapse problem, what happens? I am expecting is at step 0 that this is the my target image. So I started training. In step 0, this is producing image like this, and we are getting output like this. So this is expected, and this is the actual. After some iterations, this is expected, but this is actual. After some iteration, expected is this, actual is this. After some iteration, expected is something else, but my actual is this. That means, and in the output, I am generating similar kind of images. What we are doing? We are generating similar images. And why we are generating similar images? Just check. What happens? For example, I have this digit data set, and in the case of mod collapse problem, what will happen? My generator will generate similar kind of digits frequently. Or in the case of if I have face data, my generator G is generating similar kind of faces. Why this problem come actually? This problem comes when at the initial course of iterations, my discriminator is loose enough. Yeah, you can say that weak. So for example, uh, generator has generated some images, for example 3. Discriminator is not able to discriminate. So generator will think that yeah, I'm going good. So it will generate even more images which are close to 3. Again it will be able to fool the discriminator. Again it will generate kind of similar kind of images. So what happens? This, for example, this is the probability distribution. We have to do the probability, achieve the probability distribution like this. And what happens at this moment of time, generator G is getting quite good performance, because he is able to beat the discriminator in a very good way. So it will keep on just uh, increasing or making the probability distribution in the same area. So it will keep on generating three more real, three more uh, number of threes in a very uh, you can say high definition manner. So it is going to generate similar kind of face in a better way. So it is going to generate one face in a very good way, but it is not able to generate the diverse data set, because it was not basically challenged by the discriminator. So it kept on just generating the same kind of images, and he was thinking that uh, I am going in a good way, I am going in a very good direction. It is same like that. If your supervisor is not challenging you, you may think like that, I am going in a good direction, and you will keep on going in the same direction, and ultimately you will be just stuck into the local optima kind of things, and you will be not able to explore. So this is the kind of mod collapse problem. I hope you have got it. Now coming to some uh, real world applications of the basically GAN based models. So I have just 20 minutes remaining, so I will be a little bit fast at this moment. So in a quick way, I will just discuss some of the real world applications of the uh, basically GANs where we can use it. So basically, real world application, for example, we can use it in the image generation. We can just use in the image to image translation. So image generation means we can just generate some kind of fake images or some kind of images for data kind of augmentation kind of things. So image to image translation, that means we can also use GAN in translating one type of image to another, one type of image to another. For example, I may just convert from sketch to photo. We can use this for super resolution. For example, I can use SR GAN. So for example, if I have the images which are not of good quality, so we may use SR GAN to enhance the resolution of the images and to get the total quality of images. That is called as SR GAN. Data augmentation in case of healthcare. So for example, if we have some images and we want to generate the more realistic images of the minority class, then we can just do it using this. We can also use GAN in text generation and enhancement. So this is not only about the images. We can also use generate the text, like the models such as GPT and other Gemini and other basically platforms are generating the data using the generative AI based concept. So there are some popular types of GAN. For example, vanilla GAN, conditional GAN, DC GAN, SR GAN, and cycle GAN. Let's have a look in brief. What is vanilla GAN? Vanilla GAN is basically the original GAN which was introduced by Goodfellow in 2014. So it uses basically simple to multi-layer perceptron. So we have D and we have G. So in case of vanilla GAN or original GAN, we are using simple MLPs, multi-layer perceptron, and this is basically used for the educational purposes. That means just for basic understanding of the GAN model. However, this model fails for generating realistic images of the complex problems. So it is not that easy to generate complex and high resolution image using this vanilla GAN, that is called VGAN. So basically, where to use it? Academic and research uh, kind of problems, making some POC kind of models, that is called proof of concept. We can use these Venn diagram models. So not much suitable for the real world applications for generating complex and high resolution images. So for example, this we for such kind of applications we can use this vanilla GAN. What is this cycle GAN? Cycle GAN is basically used for image to image translation purposes, for example like making from sketch to image. So here we have two discriminators. So this was the architecture that I have discussed. It was just the basic architecture of the GAN, that is called vanilla GAN. So with the course of time, a number of different architectures have been developed by the different researchers. Some has used two discriminators, some has used two generators, some has used 2G and 2D, and so many depending on the kind of requirement. So in this case, we need to have some paired training data uh, if you want to just train it. So here we do some kind of pixel to pixel translation kind of thing. So this is the basically example of cycle GAN. For example, I have a image in domain A, and I want to generate the fake image, a similar type of fake image in another domain that is called as B. So here we can have two generators and one discriminator. So I am not going much in detail because I'm going sort of time here. So you can just go through with the literature uh, and see and check what are the other types of GAN that are available, and you can just use them. Simple, another type of GAN that is called as conditional GAN. In case of conditional GAN, we can give some condition to GAN for generating the images. That means if I have generator G, I may give him some condition that you have to just uh, produce something like black and white image, or you have to produce some image with high contrast, or you have to produce the image with low contrast. So we can give some conditions to the GAN, that which kind of image you have to just generate. So for example, I have to generate X-ray image. We can just give a condition that you have to basically generate black and white kind of image. So this is the example of conditional GAN. We can basically give some kind of things like labels, that you have to just take this input and you have to just convert this image in this particular format. So generator may be given some labels, and these labels are called as conditions, and generator may just generate the images based on that particular condition. So like we can just convert some black and white image to colored one. So like DC GAN, in the case of DC GAN, what we may do, we may just have some deep convolutional networks as a discriminator and generator. So if I want to generate some complex images, we want to generate some realistic images like some face, some objects, and some other kind of complex images, then we can use some deep convolution network as a discriminator and as a generator. So here we have to use some deep convolution network because I want to generate some realistic images kind of things. So here we can use this deep kind of networks as generator. So what are the SR GANs? SR GANs are basically used for enhancing the resolution, so it has a lot of practical applications. So for example, if we have some images and those images are blurred one, not the real one, not that much good in quality, so sending it to classifier before sending it to classifier we may just enhance the resolution of these particular images. So that is called as basically SR-GANs. So we can do it like this. We can just crop some portion of the image and we can improve the resolution. We can also do. So because why it is so? Because if I am cropping the some portion of images and increasing the size, it may be blurred enough. So if it is blurred, then we can just enhance the size of that particular images. So this was all about the theoretical part of the generative adversarial network. So I will just give a quick look of the program of this generative adversarial network. So don't have to worry. I will share the code with you. This is the sample code that I will show you. and this code is basically for generating the digits. So I will be taking MNIST data set, that is the data set of the digits. This is simple sample code. I will share the code with you. You can just go through it, and if we talk about the syntax, you can just copy the syntax and put on GTP, and just check that what is the meaning of that particular syntax. And if you are aware with the Python, so I don't think you will be facing any kind of issue in understanding the syntax. So I will be giving you the quick review of this particular code. This is the uh, GAN code for the MNIST dataset. So here I'm doing nothing. These are some of the basically packages that I'm importing, like TensorFlow, OS, NumPy, and Matplotlib for plotting the graph. So you can just check for it. You can just import it. And here what I'm doing, I'm just basically importing the data, and after importing the data, I am loading the images into the memory. I have also written the comments after each line, that what is the meaning of this particular line and what this line is going to do. So basically whatever the data I have loaded, I have just divided the data in, or you can say that we have saved the data in two variables. One is train x and one is the train y. So this is the training and testing samples for the real and fake images. So if you want to know how many images are there, so there are 6,000 training images and 1,000 testing images that I have taken. And if you just want to just check that how your images will look like, you can just plot the you can just plot the images. So what I have done, I have just plotted some images, 25 images from the data set that I have taken. So this is the basically code for plotting 25 images. So I have taken a loop of 25, and just you just pyplotlib, and I have just taken a grid of 5 cross 5, 1, 2, 3, 4, 5. So these are the 25 image samples that I have picked from the data, and basically printed it to just check that how my data looks like. Now I have two data variables. One is training and one is the this, and I have just uh, reshaped and loaded in this particular variable. This is the buffer size. What you can do, you can just, if you want to just reduce the IO, you can have the buffer of larger size that can be used to just store some images in the buffer inside the RAM, and that can basically speed up your task. And this batch size is 256. That means the data will be taken into the chunks of 256, which can be run parallelly for the training purpose. This is basically the definition of the generator model. So I have already shown you in the PPT that we start with the random noise that may be a 1 cross 100 vector of Gaussian noise, and after that what we could do, we can just reshape it, and after reshaping we will just keep on upsampling it to get the image of the required size. So this is the noise vector, and I will keep on resampling it. So reshape, and I am using this convolution 2D layer in order to upsample it, and again I have just upsampled it to 14 cross 14, and then 20 cross 28 cross 28. So what I am doing, just I am creating an image from a noise of 1 cross 100 to this 28 cross 20 image. So there is nothing to worry about. Might be possible. It seems that it is a little bit difficult, but if you think, if you want to know about the syntax, you can just copy any line and paste it on GPT or any other model, it will just uh, tell you about the syntax, what input is it is taking, and what output is going to give you. So this is the basically sample images that I have also shown you for your reference, how basically the image is generated from the noise. So this image is typically generated from the noise. The GAN is going to start with this noise, and it is going to update this particular image by the course of time. So it will start with the random noise and will keep on updating with the course of iteration. So this is the basically discriminator model. Here, discriminator is just a classifier. It is also using convolutional 2D model, and the last layer is basically is flattened from 0 to 1, and sigmoid is used as an activation function, which is going to produce the output between 0 and 1. 1 should be for the class which is real, and 0 should be for the class which is fake. So this is basically decision of the discriminator model that I have printed. Now coming to the loss of the discriminator, you can just check. If I talk about the loss, so loss of the discriminator will come from two phases. One is from the real, that is called real loss, and one is from the fake. So I have just discussed two terms. One is the A and one is the B. So these are the same two terms. A plus B is the total loss. This is called real loss, and this is called the fake loss, and see the total loss. This is the same thing, if you remember, that I have discussed in the PowerPoint while delivering the theory. That discriminator is going to receive the samples from two sources, one from the real database repository, and one from the fake sample that has been generated by the generator. So it has to calculate loss from both the points and make a sum. And this is again loss from the generator. It is going to have a single loss, because its job is to just generate the data from the noise and get the feedback from the discriminator. So these are some checkpoints that I have made. So for example, I'm running this code for the 50 pokes. So just check how we can see the output. So I have performed the training, and because I'm just overing with the time, that's why I'm just making it quite quick. So on the model of 5 epochs, I'm just running the plotting the output. And if you see the output, that after the 5 epochs, it is going to generate the images like this. After 5 epochs, like this. After 10 epochs, the image quality is little bit improved. So what I did, I trained the model for the 50 epochs, but on after 5 epochs, I just kept on printing, so that I will be able to know that how basically the training of GAN evolves with the course of iteration. So if you can check, after 20 epochs, the output is improving. Again, after the 30 epochs, output is improving a little bit more. After 40 epochs, we are able to see clearly about the digits, and after 50, even the digits are more clear. Got it? And this is a kind of TIFF file that I have generated. So it is showing how the output is basically uh, growing with the course of time. So don't worry, I will share this code with the all of you. And meanwhile, if you have any doubts, you can just ask.
Okay,
So
participants, you can write your queries in the chat box.
and if you are yeah, done, then no issues. We can just end this session. I think I have already discussed this query. That is what happen if we basically perform training simultaneously, so we will encounter the problems such as non-convergence and mod collapse kind of thing, because the loss function will basically oscillate, will not be able to converge. So I think there are no further questions from the audience. So can we end this session?
There is one question, I
There
think.
is one question. In YOLO-like model, do we need SR GAN? Like, since images are already high resolution. So if you already have the high resolution images, then why you need the SR GAN? So SR GAN is basically super resolution GAN, which is used if my images are not that much uh, if my images are not of good resolution. So for example, if you want to train a classifier and the input sample or the training data is not that much in good of good quality, or if you want to perform some kind of segmentation uh, using YOLO, you want to perform some object detection using YOLO, but the images that you have are of not good resolution, then yeah, before providing them to YOLO, you can just apply SRGAN and make them high resolution. Then your model's performance will be quite good. Yeah, anything else?
Sir,
So
I
okay.
think there are no more queries.
Okay, so let's close this session. So thank you all of you for listening.
Okay, thank you, sir, for joining us in this session. Okay, you can leave. Yes.
Okay, bye bye.
Okay, thank you, participants, for joining us in today's session. We will meet tomorrow in the next session. The participants can leave now.